Be here, right? So welcome everyone to the 2020 APAC Groundbreakers virtual tour by APAC OEC. This year, our event would be the biggest one ever done with 174 sessions, including normal sessions, workshops, hands-on labs from 123 different speakers over 11 days. These sessions also will be in 4 different languages. Please remember to register as many sessions you can, and all sessions would be available to replay as many times you want for 2 weeks after the initial session date and time. You can also interact with speakers by posting questions or commentary directly into the playback session page. And with that, we have our sponsors. Thanks to all the sponsors, many user groups, Java user groups, to make this event possible, and also to our sponsors, Oracle Groundbreakers and CloudDB. With that, today we have John with us from the Database Time Fundamentals. He's going to speak about, and please feel free to write questions at any time during the sessions in the Q&A tab at Zoom webinar. And the speaker would be answering those questions at the end of the session. Please feel to contact me at any time on the chat tab of the Zoom webinar. I will be now handing over it to John. John, up to you. I'm stopping the share. Over to you, John. Yep, go ahead. Thank you.
Okay, thanks everyone. Let me just share and move over to my presentation screen. So first, let me apologize for not looking directly at the camera because my big screen is a little bit over to the left. My camera's on the laptop, so it's a little bit funny, I know, to sort of see a speaker that's not looking at you. Anyway, we're going to talk about database time fundamentals, and this is a pretty basic presentation, but database time is fundamental to Oracle performance analysis, so it's good to just be reminded of the core definitions and why they are what they are. My name is John Beresniewicz. I'm an architect in the Enterprise and Cloud Manageability group. I joined Oracle in 2002 as part of the Enterprise Manager Group, which is kind of what the Enterprise and Cloud Manageability Group evolved from. I took some time off and I'm recently returned to Oracle as of about a year ago. So simple agenda, some basic stuff at the beginning, intro, architecture, and then we'll dig into DB time and the related notion of average active sessions, which is really what the presentation is about. We'll talk briefly about instrumentation and tools. We won't go into any real depth about that because that's a little bit more advanced. And then I plan to do a perf hub demo, but I did this presentation a couple weeks ago and had a lot of trouble with the demo part, so I'm going to just sort of skip over that. And there's enough content to pretty much fill the 45 minutes, I think, so maybe a demo would not have found enough time. Just a brief kind of note about my personal kind of history in the Oracle performance management space. You know, approximately 100 years ago, I was actually an Oracle DBA, circa versions 5, 6, and 7 of the database. Also spent time as a data modeler, which you barely hear the term anymore, but it was actually a job title. Moved into sort of the realm of performance management tools at a company called Savant, and we had a product called Savant Diagnostic Center for Oracle. So took this opportunity to show an old screenshot of our, our circa 1995 vision of what an Oracle database looks like. But we actually sort of started this diagnostic kind of language. We called our tool the Savant Diagnostic Center for Oracle, and then everybody started to become about diagnostics as of that point. So I kind of feel like we pushed the industry towards this notion of just diagnosing, not just monitoring. I joined Oracle in 2002, and at that time, Oracle 10G database manageability was a stack of functional specs about this high that landed on my desk. And myself and a couple of colleagues, you probably know Kyle Haley and James Morrow, Gaja Vaidyanatha, we were charged with exposing Diag and Tuning Pack, well, database manageability, the names Diag and Tuning Pack came later, through Enterprise Manager. And so that's really where the big part of my journey in terms of Oracle performance management started. And then just a couple of notes down here. I've been lucky enough to kind of have my career intersect pretty deeply with, you know, some of the people and technologies that we'll be talking about today, but that grew, evolved over time, you know, kind of coincident with the time period of my career. So, you know, when I was a DBA, we used to use BStat and EStat, and that grew into Stats Pack. And I've been lucky enough to know and or work with a lot of the folks that have been instrumental in this sort of technology evolution, for which I'm very thankful, actually. So let's talk about performance. So you're probably used to thinking about performance in terms of either latency or throughput measures or metrics. And these are typically time series. So we'll chart, you know, plot a bunch of points over a time axis. And latency is generally understood to be, you know, how long it takes to do a unit of work, whatever that means. So it'd be thing like a response time or elapsed time per call, something like that. And throughput is really just the inverse of that. It's basically taking units of work and dividing it by units of time. And so you're basically saying, well, how long does it take to do X amount of work? Whereas, no, I mean, how much work can I do in X amount of time? Latency is how much time does it take to do a unit of work? Throughput, how many units of work can I accomplish per unit of time? And today we're going to learn about a metric that we like to think of as the database load metric. And that is actually a measure of DB time. So it's similar to a throughput metric in that it's a measure of a metric per unit of time, per unit of elapsed time. But the metric is not a unit of work as much as an amount of time. And the time that we are measuring is database time. So that's the subject of the talk. And the name for this metric that we track, database time per unit of elapsed time, has a formal name called average active sessions. And so we're going to go into the meaning and history of average active sessions a little bit. But again, I said this was basic, so here we go. A database computes over data. Typically, data can be large and resides on disk. We want to save data over time. Compute always uses the CPU, and computing happens in the context of an executing process on the operating system. So programs execute and compute over the CPU, and they actually access data off of disk. And so they can really either be, you know, on the CPU doing computations, or they can be waiting to get on the CPU because, for instance, in this example, they may be waiting on an IO. So if they get the data, then they can compute. But disks aren't instantaneous, and so sometimes applications have to not be using CPU, but be ready to use CPU. So again, very simple diagram of the relationship of an Oracle database to an application. Okay, and so there's no attempt here to sort of unpack the application box. It can be very complex, you know, 3-tier applications, microservices, whatever. There can be all kinds of complexity inside the application box there. But from the point of view of the database, all applications request services of the database across some kind of network connection. And so the database responds to application requests in a standard sort of request response protocol manner. Now inside the Oracle database box, we have our little compute diagram. And in particular, we've labeled the process an Oracle foreground process. So an Oracle foreground process, we're going to talk about a little bit more in a second. So in terms of DB time, well, DB time is measured inside the database. Excuse me while I take off my hairbands. But application response time is measured here, right? And so one of the key reasons that DBAs need to be very cognizant and attentive to database time is that database time is part of application response time, but it's not all of application response time. And if you've been a DBA for any amount of time, you're probably familiar with all fingers always pointing at the database when there's response time problems. And so as a DBA, it would serve you well to know exactly how much application response time can be accounted for by time spent in the database. Because sometimes an application may be experiencing very poor response time, but doing almost nothing inside the database, which means the problem is not in the database. Okay. So let's just talk about DB time. What do we mean? Database time, I should maybe have spelled it out, but we always call it DB time. So sort of a casual definition would be time spent by the database processing SQL. And that's what databases do, right? From the application point of view, that seems like a pretty good definition. You know, I sent the database SQL and it spent time doing something until it gave me my answer. And so let's call that database time. Well, the kind of casual definition begs as many questions as it answers, really, right? What time are we talking about here? And what exactly do we mean by spending time, right? Time isn't bitcoins or dollars, right? So spending is sort of maybe a problematic verb. And what do we really mean by the database, in fact, right? And then processing SQL. Do we mean only queries? Do we mean any kind of SQL? Are there things that aren't SQL? So there's not a lot of precision in that definition. So maybe getting a little more precise, let's say that DB time is total accumulated foreground process time active in database calls. Okay, well, that sounds a lot more strict and rigid. But again, why did we sort of convert the first form into the second form? So let's dive into that a little bit. So database time is foreground process time, right? Well, why is that? Well, that's precisely because foregrounds are actually responsible for handling application SQL, getting answers for queries, responding to DML that comes from applications. And as we mentioned earlier, it's a component of, and usually a significant component of, application response time. And so that's why we're interested in measuring it. From the point of view of getting business done, the databases, the time the database spends actually doing the work of applications is what we're interested in. However, Oracle also has a number of background processes. Back in the old days, it used to be 6, 7, 8 of them. Now there's probably 60 or 70. I'm not sure how many, but I know there's many, many more than when I was a DBA. And these background processes are doing lots of important work. And they may be using CPU and they may be accessing disk. But the important point is that they are not supposed to be in the direct line of user response time. In other words, not background processes don't involve themselves with answering SQL that came from applications. They do all kinds of important housekeeping, but they do that behind the scenes and hopefully without impacting the important work of the database, which is answering end user queries. So we limit DB time. When we talk about DB time, we're really strictly limiting ourselves to talking about foreground process time, because that's the time spent really that end users spend waiting. But we can't ignore backgrounds altogether. And we should always remember that backgrounds are using resources, and they can actually impact response time. But those are sort of advanced cases. Usually we are pretty safe not thinking too much about backgrounds. Okay, so database time is time spent by foreground processes in a database call. Okay, so here's a little sort of call response diagram. Time is moving from top to bottom. The application is the client. It's communicating with the database through a foreground session. It sends a SQL across. Maybe it's a select statement. The database has to parse it, optimize it. These tend to be CPU intensive activities. Maybe executing involves, the SQL involves some IO. And a result set can be handed back to the client application. Maybe the client thinks about it a little bit, or some inactivity happens, and then some fetch calls, some more fetch calls. These might involve CPU and IO. So there's a lot going on inside the database between the request and the response. There's also idle time. Idle time in the database. The database sees the time between requests as idle, right? This is the colored sections here are the times in a call, and the gray sections here are the times between calls on the database side. And the same thing on the client side. Client makes a call. The colored section is then the response time, and this is client side idle time. And you can see client side idle time and database server side idle time don't necessarily match up one for one. So we said that so the definition of database time was foreground process time in a database call, and the foreground process should be active or actively waiting. Okay, so this is the third sort of component of the definition. And by active, we mean using the CPU, computing, actually engaging in computations. And by actively waiting, there's a little subtlety here, but by actively waiting, we mean ready to work, but waiting on some resource. Now, typically, those resources could be IO, in other words, waiting for data to come in to the system from the disk. Other kinds of waiting could be waiting for a lock or a latch. So this is a sort of an internal serialization mechanism that keeps, both of these are internal serialization mechanisms that allow applications to share resources by, controlling access. Well, sometimes a foreground process is ready to do something, but maybe another process has a row in a table locked, or is holding a latch that the process needs. Well, the foreground process is ready to work, but it hasn't got the resource it needs yet. So as soon as it gets that resource, it's going to compute. And we call that actively waiting. Idle time is something most people are familiar with from the SQLnet message from client wait event. And that really just means that, the foreground process is there. It processed whatever your previous request was, and it's just waiting for the next call. So SQLnet message from client is the time spent by foreground processes between calls. So that's considered idle, because from the point of view of database time, it's only time spent in the call. So time spent outside of the call is idle time, and that's not active time, so that's not included in database time. So SQLnet message from client builds up a lot of time, but you don't care about it at all from the point of view of database time. Okay, so the model of time in the database, the model of DB time, is very simple. We basically, and we've kind of already hinted at it, we think of database time as being composed of CPU time plus wait time. And by wait time, we mean active wait time, as we talked about previously, not idle wait time, like SQLnet message from client. And so, the DB time, sort of the clock starts when the call enters the database, and the clock stops when the call leaves the database, and when the response is handed back to the client. And all the stuff that happens in that time interval, with the exception of any idle time, is part of DB time. And it's typically going to be either on CPU or in wait. And now it's important to note, but it's an advanced thing, that this is really just a model, and it's only an approximation to reality. And in particular, there's a little bit of sort of bleed time there between CPU and wait time. And we're not going to get into it in this presentation, but as wait time latencies shrink, for instance, I/O, now we're measuring exadata I/O in microseconds, and maybe we'll get to nanoseconds or something, but it used to be tens of milliseconds, right? So as wait times shrink, that little bleeding area between CPU and wait becomes more and more important. But that's an advanced topic, not for this talk. This is another sort of architecture diagram, and it's a little bit maybe out of scope for this presentation, but it's basically just a reminder about the instrumentation. So all the instrumentation for DB time and various other system stats, happens at the foreground and background session level. And what I mean by that is when foregrounds, when a client makes a connection to the database, a foreground process is spawned, and then that foreground process attaches itself to one of these things called session state objects that are pre-allocated so a foreground will actually attach itself to a unused at present session state object. And that's a memory area inside the system global area that belongs to that foreground as long as it's attached to it. And all of the accounting that for DB time and system statistics happens inside that session state object and is maintained by the foreground process or background process. Backgrounds also attach themselves to session state objects. So, all the processes that are involved in an operational Oracle database are attached to one of these session state objects, and that's where all of these sort of instrumentation values are maintained. So the foreground itself maintains its database time counters, and but I won't say any more about that. Okay, so let's talk a little bit about instrumentation. I'm going to do a time check here. Okay, so let's talk about instrumentation here. Time model is an instrumentation layer that's kind of, we introduced the $V sys time model view and the instrumentation associated with that in Oracle 10G. But really, when you think about time model, it started with wait events. Basically wait events plus CPU time equals time model. But in 10G, there was a couple of pieces missing. The CPU time was not quite reliable enough in the systat counters, and so there's a new implementation for gathering CPU time from the operating system, and the counters for overall database time and background elapsed time were added. But the wait events really kind of kicked off the whole timing things in the database, which is what time model is really about. It's about turning stopwatches on and off in response to events inside the database. Most notably, the call start and the call end, which is that outer boundary of DB time. Another important thing to know about time model is that CPU time, DB time is measured in this stopwatch fashion. Call comes in, DB time clock starts, response goes out, DB time clock stops. But CPU time is different. CPU time is not clocked by the foreground process itself. CPU time is fetched by the foreground process from the operating system, okay? And so in particular, the important thing to remember about CPU time in time model is that it represents actual time spent on CPU. And in particular, it doesn't include time spent on run queue. So if you're in a CPU saturated situation, you may actually be spending time trying to get to CPU as well as time spent using CPU. But in time model, all that will be exposed is how much actual CPU time you got, or the foreground got. When I say you, I'm assuming you're a user with a foreground process. Yeah, and so $system event is where you can see wait event timing information, and $sys time model is where you can see these additional time model measurements. So just looking a little bit into $sys time model, these are really the 4 measurements that you're interested in most. The others are for, more specialized analysis. But at the basic level, you have DB time and DB CPU. You have background elapsed time and background CPU time. Now, it might be a little less ambiguous if we call DB time foreground elapsed time and DB CPU foreground CPU time, because then it would be obvious that, you got background, foreground, CPU, and elapsed. But because foreground time was sort of special, we gave it this special name, DB time, and foreground CPU is special, we give it sort of the special name, DB CPU. I'm not sure it was the best idea. I think it was probably worth doing, but I know that it's easy to forget that DB time doesn't include background time, because it sounds like it should in some sense, right? Backgrounds are database processes, so they should be in database time, but database time is only foregrounds. Okay, big concept here. This is the thing you really need to understand. And I hope that people don't have trouble understanding average active sessions, but it seems like it's a tough concept. So what is average active sessions? You'll see it in a lot of places. You'll hear me talk about it all the time if you ever listen to me talk about stuff. So database time per unit of time is what we call average active sessions. Now remember, in the case of metrics, we take like transactions per second, right? So we measure something and divide it by the amount of time over which it was observed, right? And that's what we call computing a rate, right? A velocity in a sense, a rate of change of something per unit of time. And so we do that with database time. So average active sessions, the sort of formal definition is that it's database time divided by elapsed time. So it's the amount of database time accumulated over some time interval divided by the length of that time interval. Now, it's very important that the time units must match, and that actually figured quite prominently in this, figuring out the name average active sessions. And so we also think of this measure as a measure of the load on the database. It's really kind of the average amount of activity accumulated across all foregrounds over some time interval, right? And so it's really kind of a measure of load when we think of load as the amount of application time spent in the database. And now it's also another point of confusion sometimes, because the word sessions appears in average active sessions. People tend to think of it as having to be, or that it should be like a whole number, because a session is like a person, right? How can you have 3.3 average active sessions? You can't have 0.3 of a person. Well, it's an average, right? And so, one person isn't active all the time, right? One person is active some of the time and not active some of the time. And that's true for all people. And so when we average up the active times, it comes out to a fractional number of effective active people, in a sense, right? And so importantly, the total sessions connected to your database may be much larger than the average active sessions. And that's because most of the time, in many applications, foreground sessions are idle much of the time. And so when they're idle, that doesn't count for database time. So you could have lots of sessions connected to the database and not be really accumulating all that much database time. And in fact, poor session management is kind of a classic performance pitfall. It's beyond the scope of this presentation, but it is the case. Okay, so I kind of referred to let me do another time check. I haven't really timed this presentation so well. So it looks like I got 15 more minutes. I think we'll get there. Yeah, and we'll get there and be able to have a bit of a chat, hopefully. So this business about how did we come up with this name, average active sessions, we were measuring database time divided by time from the very earliest, and we called it database time per second. Just like all the other sys metrics, we had sort of a per second and a per transaction of the measure, and the units for database time per second were in centiseconds per second. And why was that? Well, because when database time was introduced, the granularity of the measurements was hundredths of a second. Now we measure in microseconds, but at that time it was centiseconds. And so the units, as funny as it sounds, were centiseconds per second. Now we were plotting this number, this centiseconds per second number, on the performance page and top activity page, and we realized it really needed a name. It was kind of like the most important thing. I mean, it's really the time derivative of database time. That's an advanced topic, but it's an important thing. So we really wanted to give it a proper name, and so we thought about it, and we actually had more than one kind of meeting to try and figure out this name. And it seemed like it should be unitless, right? It's a time divided by a time. So then time should kind of like cross out, and then it should be sort of a unitless metric. And along the way, I can remember we had big meetings. I mean, these are meetings with 12 people, all very high level Oracle performance types, and trying to figure out a name of something, right? We already had the charts and we didn't have the name of the metric really nailed down. But because it was foreground centiseconds, I remember at one point, proposing, well, maybe it's really kind of like centi-users per second, right? Sort of emphasizing that the seconds on the numerator side were foreground or user seconds, and the seconds on the denominator were sort of elapsed seconds. And that was really kind of the thing that steered us, I think, towards the notion of average active sessions. And you can see here, this is actually a Xerox of my meeting notes from the meeting in which we actually named average active sessions. And you can see here, I wrote down after my little highlight arrow, seconds per second equals average active sessions, right? And so that was a pretty important meeting, I think, because you're going to see that term average active sessions all over the place. If you haven't already, I'm sure you have. And I think it was actually a very effective and good name, in spite of the fact that it does it takes a bit of learning to get used to, I think. Okay, so just a brief note about tools. Where does DB time show up in terms of things like AWR and ADDM? Well, the answer is all over the place, right? And sometimes in slightly subtle ways. So here's like sort of the top section of an AWR report. And you can see here, right at the very top, we've got, now remember the database average active sessions is DB time divided by elapsed time, where the units match, right? So here you can see right at the top, DB time and elapsed time, both in minutes. And so we can take DB time, 48 divided by 65, do the math in your head, comes out to about 0.75. Now, I'm not that good at math, but there's the 0.75 right down here, because top SQL statements, average active sessions of the task. So these are ADAM findings. And so ADAM findings actually is classifying or ranking findings by average active sessions. How much database time do these findings account for, or what is the impact of the findings? And even down here, this is a little more subtle, but this is in the load profile, but you can see we have DB time measured in seconds and DB CPU measured in seconds. So when we take DB time measured in seconds and we do it on a per second basis, we get average active sessions. So this number here, this 0.8, this is really this 0.75 rounded up to 0.8. It's the same number, right? And we just don't have the same digits of accuracy, which maybe that should change. And again, DB CPU, this is the CPU piece of database time. So this is average active sessions on CPU. So just by looking at 0.8 and 0.5, we can see that in terms of the load on this database, most of it is CPU, 2/3 of it is CPU, 0.5 out of 0.75. In terms of ADDM, basically ADDM's sole purpose in life is to analyze DB time and give you, the DBA, insights into how to reduce the DB time. Okay, so Atom is a big rules engine that basically focuses almost entirely on DB time and shrinking DB time. The classic sort of performance analysis is if you do the same work in less time, performance is better, right? So on the right here, you can see this is taken straight from the doc, and pretty much what I've been talking about is spelled out there in a pretty terse form. Now Atom makes findings, ADDM makes findings, and findings are categorized or sort of quantified by impact, and impact is precisely how much DB time is involved in the finding. And Atom can also make recommendations in response to the findings. In other words, things that you can do to address these findings. And the recommendations are quantified in terms of their potential benefit. And the potential benefit is expressed in terms of how much DB time can be reduced if this recommendation is adopted. So Atom is all about DB time. Okay, let's check the time again. Getting close. So ASH, hopefully everybody is familiar, at least in some sense, with active session history, which is we call ASH. And ASH is a sampling technology, but is also directed at DB time, okay? And so what ASH does is it basically, once per second, it looks through all of those session state objects that we saw and basically says, hey, is this session, one by one, it traverses the list of session state objects. They're all organized in a linked list, so it can just zoom right down. And what happens is, ASH asks, okay, right now, is the session in a database call? And if it is it not idle? In other words, is it active on CPU or is it actively waiting? And if that's the case, I'm going to write a record into an in-memory repository of these samples. So once per second, all the sessions are looked at, and all the active ones, by the DB time definition, are recorded. And what is recorded? Well, all kinds of session state values are recorded. What SQL, what PL SQL, what wait event, if it was doing IO, what object, all kinds of things. What plan hash value, what plan operation, was it actually in a nested loops or a full table scan? All of these things about what the sessions were up to, the active sessions, are written into active session history. And in particular, when you're using ASH, you want to pay attention to, especially for filtering, session type. Remember, foregrounds are involved in DB time, backgrounds don't count for DB time, but they all get sampled into ASH. And then you also often want to distinguish between sessions that are waiting or sessions that are on CPU. So just go ahead and keep those two values in mind. So what do we do with ASH? I think of ASH as kind of a magic, kind of a little bit of, I don't know, it's a magical thing to me, right? But basically, the way we use ASH is every row that gets sampled into ASH counts for 1 second of active session time. The 1 second is because the sampler samples every second. And so you can sort of think about ASH as a kind of a movie of what happened in the database over time, where the frame rate of the movie is 1 second. Every second, the camera takes a picture. and then waits a second and then takes another picture, and then waits a second and takes another picture. And what does it take a picture of? It takes a picture of all the sessions that are active in the database. Well, those are actually all the sessions that are contributing to DB time. Because if Ash wakes up and says this session is active in a database call, well, that means that session's time is counting towards database time. So we kind of use Ash in a sort of in like a movie-like fashion where, you know, the frame rate is 1 second, and basically whatever we observed is what we count a second for that state until we observe something else, right? And so what we do is we add Ash samples and we equate that to seconds of DB time. And that's kind of what's magical about it, because you're basically estimating DB time from these discrete samples of what was happening in the database. And the power of Ash derives from the fact that you know, there are so many dimensions about the session's activity that are captured. And so you can aggregate, you can sort of slice and dice DB time over some time period by aggregating Ash samples over different dimensions, right? And so that's kind of the sort of the magic of Ash, or one of the magics of Ash. And so this little query on the right just shows you in a very simple way, you know, how to find, you know, by, you know, sequels that are accounting for the most DB time in the current in $V active session history. Now, in this, you know, this may or may not be very useful, right? It would be more useful for us to compute average active sessions, because we don't know how long these DB time seconds accumulated over, right? This is SQL ID. You know, it depends on how big the Ash window was, right? If, you know, so we're not dividing by the elapsed time here. So we're just computing a raw DB time measure, not quite as useful as an average active sessions. Okay, so Ash Math in action. Everybody has used Ash Math in action because you've used the top activity page. This is probably the most popular and widely imitated page ever in Enterprise Manager. And so basically the top activity page is a picture of DB time in the database assembled from Ash data. And then if you've used the performance hub and the load map, which is this tree map on the bottom, that is also a picture of DB time. That tree map is all the DB time in this time window represented by the time slider, broken down by aggregating Ash samples by various dimensions. And it looks like here we're doing it by wait event, and then by, I think it's by SQL plan operation, and then by object, okay? And so that's a very powerful breakdown right there. We're actually showing user IO wait events, the SQL plan operations that were responsible for those user IO wait events, and the actual objects that were being accessed, right? And so we're talking about combining a view that combines a physical IO operation, DB file sequential read, DB file scattered read, with a logical SQL execution plan operation with the actual objects, physical objects in the database that are being accessed by that operation. So you can see how that's a very powerful way to be able to slice and dice what's going on inside your database. Okay, hey, that's the end of the presentation. So I think I ended pretty much, oh, looks like I got 1 minute. So check out my LinkedIn profile, and in particular, look for these two presentations that are attached to there. And these are much more detailed, advanced treatments of Ash and database time. And I guess with that, I'll say thank you. And let me look over and see whether there's any questions. I guess we
don't have any questions. So thank you so much, John, for all the time you have. And this is a great presentation. I'll stop the recording now.
Did we have anybody?
No, we have we have 2 participants. They just left.
Okay.
Yeah, we have 2 participants.